Hello everyone, I'm Brian. The goal of this work is to ensure safety in multi-UAV systems, while keeping the overall performance high. The proposed provably safe distributed control method is efficient in terms of computation and communication, and has a very good scalability to larger swarms. In the proposed framework, the control layer pre-stabilizes each robot with a state feedback law that does not account for safety constraints. In the navigation layer, each agent runs a local explicit reference governor, ERG, that ensures safety constraints by transforming the desired goal into a safe goal applied to the pre-stabilized system. This layer relies on the parallel exchange of information between agents in the local neighborhood. For a swarm of quadrotors with higher order nonlinear dynamics, the ERG considers constraints on the UAV inputs, the actuator saturations, and on the UAV states, wall, obstacle, and inter-UAV collisions. A common technique in real-time motion planning is to use a simple geometric planner to generate a nominal trajectory, which is then followed with a feedback controller. Since this trajectory will not generally be dynamically feasible, there will be some tracking error that can cause undesired collisions. To fix this, motion planners often augment obstacles by a heuristic tracking error bound or safety margin. This is often done in practice, but does not necessarily guarantee safety and can still result in collisions. On the other hand, excessively augmenting the UAV safety margin is safe, but overly conservative, preventing fast and efficient navigation in densely cluttered environments. To fix this, we propose a trajectory tube distributed ERG that in real time adaptively and minimally augments the UAV safety margin as to ensure safety. It does this by predicting a long horizon trajectory from the current robot state to the current safe goal using the pre-stabilized dynamic model. This prediction is used to compute a minimal volume invariant tube. The tube pose and geometry is efficiently communicated between nearby robots. The governor computes the dynamic safety margin, which represents the minimal predicted distance to constraint violation. And it computes the navigation field, which repels the safe goal references of two UAVs along this minimal distance direction and attracts these towards the desired goals. The ERG continuously manipulates the derivative of the applied reference, such that, for a constant applied reference, the transient dynamics will never cause constraint violations. The method does not use optimization algorithms and has an explicit or closed-form solution, which can be obtained by simply scaling the navigation field's direction with the dynamic safety margin's amplitude. In this simulation, UAV 4 safely and reactively flies up and forth through the circle on which UAV 1, 2, 3 are requested to fly. The long horizon predictions are depicted by pink lines connecting the UAV position with the safe goal reference frame. The orange minimal volume tube encapsulates this prediction. The smaller the distance between tubes, the smaller the dynamic safety margin, and hence the velocity of the reference to the controller will be reduced as well. Collision avoidance is shown in field experiments with two UAVs, where on the left they swap positions on parallel lines, and on the right they cross on perpendicular lines. The method fully runs on board an Intel NUC computer with a compute time of only 1 millisecond. On top of provable safety and increased performance with respect to our prior work, benchmarking results have shown improved scalability over priority-based distributed MPC. For more in-depth discussions, please come to the poster session this afternoon. Thanks.